Welcome to this webinar session hosted by IARPIC Collaborations, which is a platform that connects federal government researchers, non-federal researchers, and Arctic communities to work together on pressing Arctic research issues. My name is Zhuo Wang. I'm a co-lead of IARPIC Arctic Systems Interaction Team. The Systems Interaction Team aims to enhance the ability to observe, understand, predict, and project the Arctic's dynamic interconnected systems and their link to the Earth system. The webinar series is organized with several other IARPIC teams and communities. And today's session is specially co-hosted with Terrestrial Ecosystems and co-hosted by myself and Liz Hoy. Liz is a co-lead of Terrestrial Ecosystem Community of Practice. That community of practice works to develop a landscape-scale understanding of the drivers and the impacts of terrestrial ecosystem changes. The webinar series aims to explore the characteristics, mechanisms, primary drivers, and predictability for different types of Arctic extremes. In today's session, we will hear from two experts on the topics of Arctic wildfires and extreme temperatures. Now I'm turning it over to my co-host Liz to introduce the two speakers.
Thanks, Joe. Yeah, we're very excited today to have both Rebecca and Timo. We're going to start off with Rebecca, so I'll introduce her first, and after her talk, we'll have time for maybe one or two quick questions as we transition to Timo's talk, and then after both presentations, we'll have a time for more in-depth discussion based on the topics that both presenters talked about today. So Rebecca Scholten is a postdoctoral scholar at the University of California, Irvine. Within the Climate, Carbon, and Fire Dynamics Lab, her research focuses on the intersection of climate change and ecosystem dynamics, with a particular emphasis on Arctic and boreal wildfires. Using satellite remote sensing and Earth system modeling, Rebecca investigates the drivers of extreme fire seasons and their long-term impacts on carbon cycling and high-latitude landscapes. Rebecca, go ahead and take it away. Thank you for presenting today.
Thank you, Liz. Okay, I hope you can see my slides now.
Yeah,
great.
We see it. Looks good. Thank you.
Awesome. Yeah, thank you so much for inviting me, and thanks everyone for joining this seminar. I'm really excited to talk about Arctic boreal fire extremes and some recent advances that we've made on understanding the drivers and different types of fire extremes. So when I'm thinking about fire extremes, I'm really thinking of different manifestations of how fire is changing across the Arctic boreal domain, going from event level specifics, such as that we're seeing more extreme fire behavior, such as, for example, extended smoldering or more fire-induced thunderstorms, so pyroCBs that really lead to extreme spread. We're seeing fires that are growing larger across the Arctic boreal domain. We're also seeing fires that are occurring in more historically fire-resistant areas, for example, a lot of tundra burning. And then at a more regional scale, we're seeing that there is an increase in the spatial extent of fire seasons, thinking about, for example, Siberia in recent years, but also Canada more recently. And then there is this very recent increase in consecutive extremes, so where we have not only one large fire season, but actually several in a row, and carryover effects. And so these consecutive extremes and drivers of these is really what I want to focus on today, because this is like something I think we haven't really understood well enough so far, or not really looked at as well. So today I want to focus on two case studies. One is Eastern Siberia, where we've seen really extreme fire activity in 2019 to 2021. And there is a paper we published a couple of years ago on what is driving these extremes. And then, so this is what I'm going to, start with. And then the second part is going to be on the recent fire extremes in Canada in 2023 and to 2025, and trying to understand what is driving the consecutiveness of this event. So Eastern Siberia, as I said, especially the region of Yakutia, has experienced really extreme fires in 2019, 2020, and 2021. And then in this published work, we found that there is a compounding driver of this. So first, we usually have an earlier than usual snowmelt. And then second, we have an anomalous atmospheric condition that is fueling the wildfire activity. And so this atmospheric condition is a northward displacement of the jet stream. So the jet stream usually is located around the mid-latitudes here, delineated by this black arrow. But when we have extreme fire activity in eastern Siberia, which you can see here in this red dashed line, we see a northward displacement shown by orange anomalies. So the Arctic front jet, as it is termed, is then blowing along the Arctic coastline. And this Arctic front jet is very efficient at trapping Rossby waves and blocking high pressure systems. And these are shown here in pink as positive anomalies in the 500 hectopascal geopotential. So there's a high pressure system stuck over eastern Siberia, as you can see. And this then leads to persistent high temperatures on the ground that fuel the wildfire activity. And so importantly, it was really the co-occurrence of this early snowmelt together with these Arctic front jet situations that led to extreme wildfire activity. And we found in this research that actually both of these drivers are experiencing really strong changes. So we're seeing a strong increase in the Arctic front jet pattern over the Arctic or over Eurasia especially. And then that is coinciding with an earlier and earlier snowmelt over eastern Siberia. And so this tells us that actually the extremes that we're seeing are somehow connected to climate warming because both drivers are changing strongly over time. Another important takeaway of this study was that actually these two drivers are not acting uniformly over space. So what we're seeing here is a plot that shows a latitudinal gradient with a tree line at the top and then kind of moving away from the tree line south on the y-axis. And we see the influence of the Arctic front jet in red and the snowmelt timing in blue on burned area. And we can see this, that, for example, looking at the tree line where tundra fires are occurring, we see a very strong influence of snowmelt timing and not so much of an influence of the Arctic front jet. And so actually the tree line is also where snowmelt is disappearing fastest. And so this tells us that actually if we want to understand what is driving different types of fires, thinking about boreal forest fires versus tundra fires, but also, for example, peatland fires, which might be become more common in a warming Arctic boreal future, we really need to think about what specifically are these drivers for these types of fires. Another important takeaway, and this is from another study led by Wen-Chan Xu, was that overwintering fires actually contributed quite significantly, especially to the 2020 fire season in Siberia. Up to 8% of the total burning was due to overwintering fire. And this was actually quite surprising because in our previous studies on boreal North America, we always thought that overwintering fires don't really contribute more than 0.5 or 1% of burnt area and carbon emissions. And so this was significantly larger than we actually expected. And so this hints at that actually these consecutive extremes might be connected to so-called carryover effects, such as overwintering fires, where one large fire season can kind of perpetuate the next one. All right, so this is kind of what we learned about Eastern Siberia. And so at the time when these triple extremes in Eastern Siberia were occurring, we were still thinking that this is maybe just a freak occurrence. But then fast forward a couple of years, and we're seeing the same thing happening in Canada. So 2023, I think a lot of people remembered was really large, but then 2024 and 25 were also pretty large fire seasons. And so that made us think that actually there might be some underlying drivers of this consecutiveness that might help us first of all, predict these extremes better, but also maybe help us alleviate some of these negative effects of consecutive extremes. So let's look at Canada. So just a quick recap of this event. What you're seeing here on the left-hand side is the burnt area in 2023 in green across Canada. And then on the right-hand side, you see the seasonal evolution of burnt area compared to 2012 to 2022 in these gray lines. And you can see this was really an exceptional fire year. Then looking at 2024, we see a lot of burning again in the west. And this was not as big as 2023, but it was still relatively large compared to historic levels of burning. And then 2025, again, even surpassed 2024. And again, we see this large burning in the west and center regions of Canada. So 2023, there was actually a lot of research on this extreme fire season, but there hasn't really been a lot of research in trying to understand why we have had three large fire seasons in a row. I think usually we think of the boreals as being a region with relatively long fire return intervals. So seeing three really large fire seasons in a row would be not what we would expect. And so thinking about potential hypotheses of what might be driving, we came up with three. The first one being that there is an underlying multi-year climate anomaly. The second would be that there is a larger contribution of carryover effects, and one part of this would be to understand why that might be. And then the last one would be that there is some kind of self-reinforcing feedbacks where one large fire year might lead or might carry on into the next or might precondition the next year. So here you can see the three hotspot regions we delineated, which I'm calling West, Central, and East, and these comprise 80% of the burning in these 3 years. So if we just look at the burned area, we can see that we have these consecutive extremes in the West in blue and the central regions in orange, but not so much in the East. So West and Central is what we're going to focus on in the following. So one big thing we found was that there is actually a connection between a hydrological drought, which we can measure through Gray's water storage anomaly, and this extreme burning in the West. And so here you see this Western hotspot region delineated by this dotted line. In the middle, I plot the burned area monthly from GFET, and then at the bottom, the carbon emissions. So you can see these recent years in green, red, and blue. And at the top, you see the Gray's water storage anomaly. And Gray's is a satellite that measures gravity anomalies, which are related to water storage in terms of snow, but also groundwater. And so we are seeing this really strong dip in the end of 2022 and then low values throughout these 3 years. So usually when we try to predict burned area in Arctic boreal regions, but also in other regions of the world, we use fire weather indices, or an easier way to do that is the vapor pressure deficit, which is shown here on the right-hand side scatter plot. So we have summer VPD versus the logarithm of burned area across these three regions, and you see this really nice kind of linear relationship. But what we found was that especially in the West and the central regions, the extremity of values was better expressed through the water storage anomalies. And this is what you can see on the left-hand side. So here you see the May water storage anomaly from Gray's versus the annual burned area for these three regions. And so indeed, if we put these two together, then adding May water storage anomaly to VPD enhances burned area predictability by up to 30% in the Western regions compared to, just VPD only. And so what this tells us again is that we have compounding drivers. We have this top-down effect of like summer heat, but then we also have this bottom-up effect of a longer-term drought that is preconditioning these areas for more burning. We also found that drought is really enhancing fire activity along multiple dimensions. So here on the left-hand side, you see this plot of May water storage anomaly against burned area. We can also see this when plotting water storage anomaly against the fire season start. There's a strong linear relationship. And you can see that, again, especially these recent years in the West and Central regions really pop out as having a very early fire season start. And we could also show that there's a linear relation between this May water storage anomaly and the number of overwintering fires that are occurring, especially again in the West and Central regions of Canada. So looking a little bit more into these overwintering fires, here's an example for Western Canada, where this red star is. In 2024, what you're seeing is in gray the old fire from 2023, and then the pink crosses indicate the locations where overwintering fires have emerged. So these we can detect because they're always starting at the rim of an old fire scar. And then the colored areas you're seeing is the fire progression, 12-hourly fire progression over the season. So we can see they start as early as May, but then can burn deep into the mid of summer until end of July. Looking at a larger region, we can then assess the contributions of overwintering fires. And here's just an example for a larger region in Western Canada. We see here the burned area in 2023. and then the new fire ignitions in 2024. And all the green crosses are those that are occurring at the edge of a 2023 fire, so are potentially overwintering fires. And if we color the new areas by their source, we can see that actually most of the burned area is still stemming from 2023 burned area that has sustained throughout winter. That's shown in green here. And then we can go back further into 2025. We now have burned area from 2023 and 2024 as potential sources. And what we can see in 2025 is that we have new fires starting on the 2024 fire scars in red, but also still at the rim of 2023 fires. And so again, these burned area associated with 2023 overwintering in green and 2024 overwintering in red contributes actually most of the burned area in this region. So in total, we found hundreds of overwintering fires that we could detect from the satellite in 2024 and 2025 in Western and Central Canada. And in total, they burned more than 3 megahectares of burned area. And just for comparison, an average historical fire season in Canada is about 2.5, 2.6 megahectares. So this is more than an average fire season. And so in the West, for example, this translated to 30% of the burning in 2024 that was due to overwintering fires. And so if we kind of look at all of North America, we can then see that really contrary to our prior belief, these overwintering fires can now contribute significantly to large fire seasons. So you see overwintering burnt area here in orange, and you can see this significant contributions to 24 and 25. And the reason we think that this is suddenly happening is kind of in the locations that we find these overwintering fires. So here you can see a zoom in of these areas where we see recent burning, and in gray you see the peatland areas outlined. And so actually a lot of the burning in 2023 happened in peatlands, and especially a lot of the overwintering happened in peatlands. And so what we're thinking is happening is that the drought, this hydrological drought, leads to a lowering of the water table in peatlands, which then exposes the peat to burning and to smoldering and leaves higher chances for overwintering and also for a spread of overwintering fires in the next season. And then this is just a little side note that overwintering fires really induce an early start of the fire season, and we can detect them, as you can see here on the left-hand side, as early as January. They contribute especially, this is what you can see on the right-hand side, to burning in May and also partly in June. And so there is this potential, since they have some predictability. We know that they emerge at the edge of an old fire scar in these kind of dry peatland areas or drained peatland areas. There's this potential to put them out earlier and prevent some of these negative effects that we are expecting from consecutive extremes. And so here, just in summary, there's a little schemata of how we think this hydrological, or like the different pathways that this hydrological drought takes towards fire extremes. First, we have this overwintering fire route where a lower water table leads to a higher overwintering survival, which leads to an earlier start of the fire season. And then we have this pathway that goes via an earlier snowmelt, lower snow water equivalent, and then kind of the Siberia pathway where we have earlier snowmelt and then earlier drying of fuels, higher VPD that then leads to, on the one hand, an earlier start of the fire season, but also more ignitions in general and higher potential for faster and more synchronized fire spread. Yeah, and that brings me to my conclusion. So there's different manifestations of these Arctic boreal fire extremes. At the event level, we are seeing more extreme fire behavior, fires growing larger and occurring in historically fire-resistant areas such as tundra regions, but also maybe some peatlands. And then on the regional level, we have a larger spatial extent, but also really importantly, these consecutive extremes. And to be able to better predict these types of extremes, we really need to understand compounding climatic factors, the diverse effects of sustained drought, and then also potentially, I haven't touched upon that, but I'm happy to talk more about that, self-reinforcing feedbacks. And I think one major takeaway was also that a lot of these kind of univariate fire danger indices that we're using might not really accurately capture such bottom-up constraints that we're seeing in such compounding climatic factors. And so there's really a potential to develop better predictors for fire activity. And with that, I'm going to thank you all for listening, and I'm going to stop and take any questions if we have time.
Thanks, Rebecca. Does anybody have a quick question for Rebecca? If not, that's okay. We'll have a longer discussion after Timo's turn. Okay, I don't see any quick questions in there, so we'll hold questions for the end to have a more of a discussion. So next I'm going to introduce Timo Vihma. And Timo is a research professor and the head of the Polar Meteorology and Climatology group at the Finnish Meteorological Institute. With a career spanning over 3 decades, he is a leading expert in Arctic and Antarctic meteorology, boundary-layer processes, and the linkages between polar climate and mid-latitude weather. He's led numerous international research initiatives, including projects focused on sea ice, snow, and the polar atmospheric moisture budget. So thank you for joining us today in this series on Arctic extremes, and I'll let you take it away.
Thank you, Tony, for the introduction. So I will speak about the extreme air temperatures in the Arctic. This talk is not based on any single study, but more like a small review based on literature from different points of view, addressing the occurrence, trends, and drivers of extreme air temperature events. Can go to next slide. Yes, some 6 years ago, we made a review on extreme events in the Arctic, led by John Walsh, and the review addressed several types of extremes in the climate system, and we evaluated the level of confidence on future changes and a level of evidence for past changes for different variables, and there were only three variables where there was highest evidence for past changes and highest confidence for future changes. These were air temperature, rapid sea ice loss events, and coastal erosion. And so now I focus on air temperature only. Next slide, please. So here we have annual cycles of daily 2-meter air temperatures over a period starting from 1940 on the basis of ERA 5 reanalysis. And we see that in winter there is much more variability and the extreme events deviate much more from the mean values compared to summertime. And we also see the decadal increases in air temperatures over all seasons, but also in that case, much more in winter compared to summer. And soon we will talk more about these seasonal differences as well. Next slide. So when climate is warming, there are more warm extremes and usually less cold extremes. And this study by Jiangdong Chang et al. Last year, it demonstrates how the probability density distributions of daily 2-meter air temperature has changed from the period of 79 to 2000 to the period of 2000 to 2024. And we see a clear shift towards warmer conditions, and it's also seen as increasingly warm extreme values when everything is averaged over the circumpolar Arctic north of 75 degrees north. And if we look at monthly extremes, we see increasing occurrence of very, very high extremes for January and February monthly mean air temperatures in the circumpolar Arctic. And An exception to this occurrence of more warm extremes are conditions over the ice-covered Arctic Ocean in summer. So here I looked at in situ observations from drifting ice stations since 1950. And then since 1950, 1991, there were these Russian ice stations whose data are presented here on the gray or black line with gray shading representing the range of variability on these data sets. And then these red is the Shiba ice station in 1997-98, and the blue is the Para ice station in 2007. And we see that in wintertime and late autumn, there has been clearly much more extreme warm extremes occurring in these two later ice stations, but in summertime there is no difference. No remarkable summer extremes appear, and there is also no trend in summertime because as long as there is ice and snow and the surface is at the melting phase, also the 2-meter air temperature is very closely tied to close to the melting point of snow. Let's say it varies between +2 and -2 degrees, basically. We can go to the next slide. And considering terrestrial Arctic, there has been strong increase in heat waves. This study by my colleague Mika Rantanen demonstrates in these upper plots how the strength of the heat waves has increased between decadal periods 1950 to 1979 on the left and 1993 to 2022 on the right. So maximum heat wave magnitude index has increased practically everywhere. And then also the fraction of surface area in terrestrial Arctic that has experienced at least one severe extreme or very severe extreme or very extreme heat wave, it has also increased a lot. We see the numbers there in the middle on the green, violet, and yellow colors for severe, extreme, and very extreme heat waves. And in addition to the trends, there is also a very large interannual variability in the area cover that has experienced different categories of heat waves, severe, extreme, or very extreme, that is illustrated on the plots on the down. So for the fraction of land area and for the ratio of land area relative to the reference period 1950-1979. So both large interannual variability and strong increasing trends. Next slide. And if we think about the drivers of warm extremes in the Arctic, basically three important drivers: cloudy skies, strong winds, and warm air advection from the south. And if we compare conditions during cloudy skies and clear skies in the winter Arctic Ocean, we see that in cloudy conditions the temperatures are on average something like 12-13 kelvins higher than in clear sky conditions. And during strong winds, the temperatures are also about 12, 13, even 15 degrees higher than in conditions of light winds. But to get really extreme values, we typically also need warm air advection from the south. And in winter, it's the warm oceans that are the most important source for warm air advection, but in summer it's the warm continents. This plot on the or map on the right shows that there are warmer air is closer over the continents than over the oceans. If we look at mean 2-meter temperatures, but even more important is that on terrestrial areas in summer, there are also very extreme events there. So, for example, on the Siberian coast, the air temperature maybe in individual days it may reach 25-30 degrees, and therefore these continental areas are very important to generate extremes over the ocean as far as we don't go over the sea ice, where the extremes are reduced due to the surface maximum surface temperature of 0 degrees. And if we think about the drivers of cold extremes, clear skies, weak winds, and absence of southerly winds are the most important factors. Except that winds from the colder continental regions may contribute to cold extremes over the central Arctic Ocean. So we have lower temperatures in eastern Siberia and northern Canada compared to the sea ice region. And in such cases, if advection is from those regions, also the southerly advection may contribute to cold extremes in winter. But in winter is mostly the weak winds and clear skies that are important for cold extremes. We can go to next slide. Yes, and what is then generating this advection to the Arctic? So very important are large-scale circulation patterns, above all blockings, that guide the cyclone tracks and themselves generate anti-clockwise, clockwise circulation to bring warm air to the Arctic, among others due to the Greenland blocking. Greenland blocking was important for this first ever rain event on Greenland summit in August 2021 that we addressed in a case study where very warm, moist air masses were advecting along the Davis Strait and Baffin Bay, and then turned east to the summit. But also, if we look at the individual daily anomalies, according to my investigations, the largest daily 2-meter air temperature anomaly over Arctic sea ice occurred on 23rd of December 2010, when the 2-meter air temperature anomaly was about 26 kelvins. And that was also associated with a strong Greenland blocking event. Or it was kind of a Greenland baffin blocking. So often the Greenland blocking also extends farther to the west. So that also the baffin area is part of the blocking. And in addition to this trajectories guided by the blocking, there was also a lot of adiabatic heating due to subsidence that is illustrated in these graphs below the trajectories. So
In that communication, we know that there are some roadblocks to that in terms of.
Okay, next slide. And okay, blockings also guide cyclone tracks, and cyclones are important in bringing sensible heat and or dry static energy and latent heat to the Arctic, as illustrated in these maps for the Svalbard region. And looking at cyclone statistics in the Nordic seas, we have found that During the period of 1979 to 2016, there has been increase in cyclone activity on those two boxes on both sides of Svalbard, but simultaneously decrease in cyclone activity in the southeastern Barents Sea, so that the cyclone tracks have become more meridional. And this seems to be associated with Ural and Scandinavian blockings that have become quite common and possibly also stronger. And next slide. And one important aspect in extreme temperatures, and in particular in the impacts of extreme temperatures, is the persistence of weather. Already more than 10 years ago, we have speculated that the Arctic amplification related to these temperature increases in the Arctic, it results to higher geopotential heights in the Arctic, weaker geopotential height gradient, and therefore weaker westerly winds in the northern mid-latitudes. And that would favor wavier jet stream and occurrence of blockings. And if so, then the weather patterns typically move eastward more slowly, and that would favor extreme weather that is related to the persistent weather patterns. And then recently we found more quantitative evidence on these changes. This paper by Graversen et al. Was published just a few months ago, and we see that there are changes in surface air temperature and zonal mass flux and 500 hectopascal geopotential height. And then simultaneously we observe changes in persistence of temperature anomalies. In particular, if we look at the number of days in anomalies lasting at least 3 days, annual number of days with such persistent anomalies. And we see, comparing these plots, that the persistence has increased mostly in regions with decreased zonal mass transport. So that it kind of confirms these more qualitative thoughts about this idea presented by Jim Oweland et al. Already longer time ago. And next slide. And in addition to what happens in the day or week of individual extremes, how is the dynamic situation at the time of the extremes, so a little bit before it. Preconditioning is often very important for temperature extremes. So in August 2024, there was a kind of astonishing record warm August mean temperature. Already in 2023, there was a record that was about 8.3 degrees, but in the following year, 2024, the record was more than 11 degrees. So the previous record was beaten by a record large margin. And this was very much related to persistent weather patterns during the entire summer, and these persistent patterns generated very high SSTs and preconditioned for the August record conditions. That included also a daily record of more than 20 degrees in Longyearbyen. And already in June, so here we have 3 columns, June, July, and August from left to right. Already in June, there was a strong mean sea level pressure anomaly between Iceland and Norway. and that favored transport of warm air masses and transport of warm surface waters to the region between Norway and Svalbard. And it contributed to the SST anomalies, so that already in June, in the lowermost right, we saw high positive SST anomalies. And then in July, the circulation patterns were not quite as favorable, but there were negative anomalies in cloud fraction that further contributed to heating of the waters in the Norwegian and Barents Seas. And in August, finally, there was a very strong pressure anomaly that contributed to southerly winds towards Svalbard, associated with negative cloud anomalies, so more solar radiation heating the sea. And then it resulted to very, very strong SST anomalies in August. And when during these most extreme days, warm air was transported from northern Scandinavia towards Svalbard, and it cooled on its path to Svalbard, but the cooling was much weaker than usually because SSTs were so high. So this monthly scale preconditioning was very important for these both August record and individual day record warm conditions in Svalbard. Next slide. So if we think about the future, in a recent review paper by Chang et al., we looked at the CMIP6 multimodel mean results for the probability density functions of winter monthly surface air temperature anomalies over the North Atlantic sector of the Arctic in three 30-year periods, and we see that the distributions are expected. They have changed from 1980s or this 30-year period starting in 1984, and they are projected to change further in the period that will end in 2045 and even more by the end of the century. And these global winter temperature increase according to CMIP6 multimodel results, it has also quite a high correlation between these extreme monthly temperature anomalies in the North Atlantic sector of the Arctic. Next slide, please. And then, of course, there are a lot of challenges in predicting individual extreme events. And, well, the climate models include challenges in predicting the future occurrence and magnitude of extreme events, but then the numerical weather prediction models have large challenges in predicting individual events. So there are different error sources in numerical weather prediction in the Arctic related to data assimilation and related to parameterization of subgrid scale processes that are complex, for example, for Arctic mixed phase clouds, for cloud radiation turbulence interactions, and above all for stable boundary layer turbulence and its interaction with waves. And it is very well known in the numerical weather prediction community that typically the highest 2-meter air temperature biases occur when there is cold conditions and high, strong temperature inversion close to the surface. And here is just one example on what has been the situation in Finnish Lapland, for example, basically for all models. Here is just that example, this NCEP CFS model. And although this study is quite old, the situation is not really better nowadays. Yes, I think this was the last slide. Yeah, thank you for your attention.
Thank you, Timo. Does anyone have any questions directly for Timo or Rebecca? And then we can kind of do some synthesis questions too. I'll let folks guess. Yeah, James. Make sure you unmute yourself. There you go.
Nice talk, Rebecca. One comment is I think the major wildfires in Canada in 2025 were later in the summer than the earlier years, and that seemed to go more with the warmest temperature in the annual cycle locally rather than something more complicated. Maybe you want to comment?
Yeah, thanks for that comment. I think so. Usually there's a bit of there's like this is like this compounding driver thing, right? Like you have the ignitions, but then not all of them will pick up. So even if you have early ignitions, it can be that you still have most of the burnt area later in the season because the spread will happen when it gets driest, right? I don't know if that relates to your, but I think so. These, for example, these overwintering fires, they're already smoldering for months. So they can smolder well into June, for example, as well, and then pick up really in June, July, sometimes even August. Like in the example I showed, for example, you could see that there was this in 2024, there was this first push in May, and then they were stagnant for a couple of weeks and pushed again in July. And in June, not much happened. I don't know if that kind of gets at what you mean. So I think the drivers of spread can be very different than the drivers of the ignitions, if that makes sense.
Thanks.
We also have a question from Rosemary, I think for Rebecca in chat.
Yeah, so Rosemary says, I watched the plants change and long grasses increase, and she worries about the spread of fires with that. And she says, with the long grasses increasing, do we have heat bowls occurring?
I mean, so grasses definitely can induce, I think, fast fire spread, and we have seen that. I mean, we're seeing that in the boreals. We're also seeing that in other regions, right? Like so, the recent extremes, for example, in Hawaii, were really driven by grasses and winds. I'm not really an expert in vegetation change in the Arctic. I see that Mike Laurenti is online. Maybe he wants to comment on that. He would be maybe the person to ask. But definitely, I think vegetation change and fires in the Arctic is like that's one of the big unknowns as well. It's really hard to track what kind of vegetation changes are occurring.
Okay, well, oh, did you have one? Oh, here we go. I see a question online.
Yeah. We have a question.
Shandong,
No,
did
yeah.
you want to say your question?
Hello, it's me, right?
Go ahead, yeah.
Oh, okay. Yeah, I have a question for Timo. During the ICARP for discussion and research planning, we had a lot of discussions about observational gap, especially during winter time over the Arctic. According to what you just mentioned, there is a big bias in satellite observation. There is also the for bias in forecast model. So winter season will be very critical because there's not much in situ observations over there. So do you have any comments for example, for next IPY5 and for next decades, if there's any way to improve observations during the winter and fill out observational gap?
Well, certainly there will be a lot of field activities during the IPY 2032-33, but it's really difficult to say what will exactly happen. But I have the feeling that drones will play an increasingly important role in making observations over the Central Arctic in the future.
Okay. Okay. Yeah. There is a bigger, in your presentation, you mentioned the boundary layer, the stratification or temperature inversion influence prediction model very much. Is there any way to improve that? I know there's a big bias, especially during the winter time for buoyancy. There's a warm ocean temperature over there. Right. So if there's any progress currently for improving that.
Mm, I have not yet seen any results of the progress, but I would guess that now when there is increasing more attention to combine numerical weather prediction models and AI-based forecast
Oh,
models,
oh,
perhaps the latter could be helpful in correcting these rather systematic warm biases that occur in conditions of strong surface-based temperature inversions and very stable stratification. I don't have a solution in mind, but I would guess that there will be some advance in combining AI-based and numerical weather prediction models.
mhm. Okay, thank you very much. May I have one more question to Rebecca?
Go ahead, 向东.
Okay. Yeah, my question is, Rebecca mentioned when polar jet stream move northward, there'll be the increasing chance for wildfire, right? So what's behind that? What's the mechanism or physical process behind that?
Yeah, that's a good question. So I think the way we're thinking about it is that if you have this polar jet moving towards the Arctic coastline, you often have a double jet state together with a subtropic jet. And that can kind of trap Rossby waves. And then you have more blocking over eastern Siberia. And there's actually another study that found that these double jets also lead to more blocking over Scandinavia, so over Europe. Like in the plot that I showed, you can really see this wave train where you have negative anomalies, so colder air over Western Siberia, and then more high pressure systems over Eastern Siberia and Russia. And so it's really the trapping of Rossby waves and then increases in blocking that seem to be kind of the way that this acts.
Oh, okay, okay. That's quite interesting. That means both subtropical jet and the polar jet, so move northward and the confined raspberry waves in that zone, right?
Yeah, so it's kind of
What do they
splitting
mean?
basically. The
Yeah.
jet stream splits up into a subtropical part and an Arctic part.
Okay, okay, okay. Yeah. Yeah,
So
thanks.
they're also
It will
called, in
be
some regions,
interesting
they
to
call them
take a look. Yeah.
split jet states as well.
Okay, okay. Thanks. Mhm.
Rebecca, I have a related question. You discussed the snow melt and the Arctic frontal zone. Do you treat them as two different independent factors, or the snow melt would affect like land sea thermal contrast and also the Arctic frontal zone?
Yeah. Yeah. So we also looked a little bit into as to whether they were connected because we expected that maybe an earlier snowbelt could also affect the atmospheric circulation, but it seems to be that it's actually more the sea ice that might drive the Arctic front jet. So the correlation between an early snowmelt and then occurrence of Arctic front jet was actually rather low. So they seem to be largely independent in a way, if that answers your question. We didn't specifically look into how the Arctic front jet is occurring, so what is driving it. There is some suggestions that sea ice might be at play, but I haven't really looked into it. But yeah, so the correlations between snowmelt and Arctic front jet were relatively low.
That's interesting. One more quick question. How far in advance can we predict like whether the season will be like an active fire season?
Yeah, that really depends where you're at, I think. I think in Alaska, for example, they are having relatively good subseasonal predictability, also looking at sea surface temperatures and sea ice. I'm in Canada, I don't know, because you don't, so it's not like in the tropics where you have large scale like climate modes like ENSO, and you can say, oh, if it's an El Nino, then that and that will happen. You know, we have some indications from like the PDO and maybe the Arctic Oscillation or something like that, but generally, I think the predictability is not as high as in some other regions of the world.
Okay, thank you. I think Jim has one more question.
Now, for Rebecca, the increase in Canadian fires after 2003 is just, or 2023 is real dramatic. Do you think that's more related to memory or the blocking patterns?
Yeah, so I think it's my guess would be it's a combination of both. I think there is this self-reinforcing feedback that if you have a drought going on, that might actually reinforce blocking and then divert precipitation from the areas. So when we looked into this kind of water storage anomalies from GRACE and tried to model them, we found that they were actually mainly predicted by precipitation decrease. So there was no precipitation over Western or less precipitation over Western Canada. It was less of an evapotranspiration effect. And so it could be that it's actually blocking that is, as Timo said, that it's kind of averting or diverting precipitation going in, and that is kind of self-reinforcing. And so by that being a memory effect, it could also be some underlying driver that there is like something, I don't know, sea surface temperature, something sea ice temperature that is kind of leading to a kind of prolonged anomaly, but we haven't really found anything. Like the PDO, for example, it can't be because it's actually, yeah. So I don't know. I don't know if that answers your question, but
Yeah, one paper says it was the PDO, but I think that's a stretch.
yeah, I think it actually switched, right? So
Well, the PDO has been really strong for strongly negative for a decade. So
yeah.
Well,
Yeah,
this
I don't
has
know. I
been
feel like, yeah,
a
it's
really
hard
great
to, yeah.
discussion. And I just want to say thank you all for having it. It looks like it might have even stimulated even more discussion. So I really appreciate everybody spending their hour. And I guess if we have other questions for our speakers, you can find their information on the website. And we hope to have more of these talks too. But I want to make sure we stick to our hour. And thank you everybody for coming today. And I think there will be more presentations in this series over time that the Arctic Systems team has been organizing. So thank you all so much.
Thank you for organizing.
Thank you, Rebecca.